Kinetics in a nutshell. What is kinetics? It basically studies the rate of a reaction, and rate is basically speed. So how fast a reaction occurs. Things that impact that are the speed that the particles are moving, the location where the two particles collide, what state the substance are in. There's a whole bunch of variables that go into determining how fast a reaction occurs. We'll go into each one of them. So first thing, let's talk about the factors that affect the reaction rate. So first, size of molecules. If you look at these four different sizes of an Alka-Seltzer, hopefully you realize the one that's going to dissolve the fastest is this one, the one that's in powder form. The reason it has more surface area. More surface area means that waters that are able to more easily interact with more particles at one time because they're all spread out. Instead of having just the outside edges or the tops involve itself with water, more of the particles are being able to interact. So this will dissolve the fastest, and that's because bigger surface area. Temperature. If you make the molecules move faster, you have more collisions. What you also do, you increase the chance that the molecules have what's called the right activation energy, which is a fancy way of saying energy you need to start the reaction. Every reaction has a set amount of energy you have to put in to activate it. And the reason is because you have to break bonds, right? When you are changing from reactions to products, you also have to break bonds on the reactant side. And because of that, you also have an activation energy. That value is impacted by temperature. Because if your solution is at a higher temperature, more molecules will have that energy ready to go to start the reaction. And there's also more collisions. The more times you have molecules colliding, the better chance of having a chemical reaction. That's what a chemical reaction is. Two things have to collide with each other to create that possibility. Catalyst is something that speeds up a reaction without being used up. So what catalyst basically looks like, and what you have to want to think about it, it arranges molecules in the proper orientation so they can react. So it encourages in what's called an effective collision. That means the molecules interact with each other at the right location. So that's what a catalyst does. And finally, concentration. What concentration does, the more chemical you have, the more chance for an effective collision. If you just have, 3 blues and 3 reds here, it's going to take a while to get the reaction going. You'd think it'd be fast, but it's not. Whereas here, you have a higher chance because there's more possibility to have collisions. So the more collisions there are, the better chance of having an effective collision and a chemical reaction occurring. So high concentration increases the odds of that. Max Boltzmann distribution is basically a graph that shows how many particles in a sample of a particular speed. You'll need to understand how to use it. And the way you want to interpret it, the y-axis tells you the number of molecules, the x-axis tells you the speed. So the average, or the most probable speed, is here. But here's the fascinating thing about this. What this really shows you is that gas particles are all over the place in terms of speed. There are some that are close to zero or at zero in terms of speed. There's some way, way above what you expect it to be. So whenever we talk about the speed of molecules, we're going to actually be talking about the average speed. Why? Because you have these outliers, and you have them obviously around here too. So this graph shows you that one, as you increase the temperature, actually increase the speed, you get something like this. And this is something you'll see. The second graph, or the second hump, if you will, is always going to be lower than the first. Just like if I go the other way, it'll look like this. It's a product of the way the graph is designed. What you need to understand is that as you go to the left, this narrows up into a smaller looking mountain. As you go to the right, it flans out. What's the significance of this? Well, this tells you that as you lower the speed, and it depends on what the conditions we're talking about. Let's say we're talking about different temperatures, right? Let's say this was at 20 degrees Celsius. Let's say this was at 30 degrees Celsius. Let's say it's at 50 degrees Celsius. What this is showing is as you increase temperature, you increase speed. And on average, the average speed is right here, here, and here. And that's what you're usually focusing on, the average, not the speed of individual gas particles, because they're all over the place. There's no rhyme or reason to it. Number of particles on the y-axis and the speed is on the x-axis. So we already talked about that. All right, this is different gases. Instead of one gas at different temperatures, you have 4 different gases. So remember what I showed you earlier, how as you go to the left, the hump gets narrower and narrower. That's what this is showing you. So what this is also showing you that the most common or most probable speed for these gas particles is right there. So if I were to ask you what is the most likely speed, you'll say about 300 meters per second for this one. What about for this one? No, let's call it about 390. For this one, that's about 450. And for this one, say about 580. Now, a lot of people screw this graph up because what they interpret is that the higher the peak, that's the one that's going to have the fastest speed. They misinterpret the x versus the y-axis. Please understand the x-axis only tells you the number of particles involved. It does not give you any kind of average or most common speed. So according to this graph, the one that's going to move the slowest is going to be the purple one. What is the purple one? C4H10O. If you can do the math really quickly in your head, you realize this actually has a smaller mass. Do we expect the one that has the biggest, smaller mass? Not smallest. Do we expect the one that has the biggest, smaller mass to move the slowest? Yeah, that's exactly what we expect. The bigger it is, the slower it moves. So which one do we expect to be the fastest? Well, the one that has a smaller mass. So if you do the math real quick, the first one is 32 grams per mole. This is 17, this is 44, and this is 58. So we expect the fastest to be the red line, which is ammonia. And sure enough, the red line is the fastest. So a couple of things you want to pay attention to. Higher temperature means faster speeds. Also, smaller molecules means faster speeds. This one is temperature. You can see it's 120 and 600, and it's the same molecule, but different temperatures. So which one do you think is going to be moving the slowest speed? Obviously, the one at 100. Not rocket science. Green will be the next. Then, of course, the purple. And once again, notice the curve. You see how pretty narrow, gets a little wider, and still wider still. And that's the way it always behaves. All right, calculating rate of a reaction. How do you do it? You basically measure the change in concentration over time. So in this situation, the average rate for this is going to take the change in concentration of subtracting these two together, dividing by the time. Now, one thing I want to make clear, when you're talking about reactants, the rate should always have a negative value. Why? Because you're losing that chemical. The change in concentration over time should be negative. You're not gaining reactants, you're losing reactants. So on the flip side of that, that means the product will always have a positive number because you're always going to be gaining. And stoichiometrically, they're all related. So the rate of disappearance of this is equal to exactly the rate of appearance to that. Why? It's a 1-to-1 ratio. What if this was 2-to-1? Well, then the rate would be twice as fast. That's how this works. That's where the conceptual angle on this occurs. So concentration reactions always decrease over time, so rate will include a negative sign, just as I showed you. So here's the math in case you're wondering. Did the subtraction, so my rate is going to be negative 1.9 to negative 4 molar per second. Why molar per second? Because the unit for concentration is molarity, and if you notice, the time is in seconds. Could it be minutes, hours? Yeah, it could be whatever unit for time they want to use. But it's always going to be molarity per unit of time. The big thing you want to pay attention to here is the change in concentration over time. And you should also recognize that as you go down, what happens to my rate? You notice I get smaller, same exponent, but smaller coefficient. So your rate slows down. You're probably like, why does it slow down? Well, think about it. As your reaction proceeds, you're going to produce more and more product, right? So instead of having just reactants available to collide with each other, now you have products getting in the way. And as a result of that, an collision could occur between a reactant and a product instead of two reactants, which is not going to create anything. So that's why your rate slows down over time, because you have products getting in the way. Rate is not constant, decreases over time. And you can see here graphically what's going on. You see how this one goes down. So what do you think this is? Try it. It's a reactant. How do I know that? Because reactants always go down over time. It tells you decomposition. That's kind of the other hint of NO2. And guess what the blue and red line are? They're your products. You notice how this is produced more than this. They're not equal lines. So you can assume the ratio of NO to O2 is different. There's more NO being produced per mole of O2. I could hypothesize it's like a 2-to-1 ratio. It could be a little more, a little less, but I know it's bigger. And that's something you have to interpret. When you see a graph and you see that the rate of one is higher than the rate of the other, that means you can assume that the other product is being produced at a higher quantity. And why is that? Stoichiometry. That's where stoic comes in for this. So you can actually use the stoic ratio to determine that. And that's what we're talking about. Determining rates based on chemical reactions. So rate of disappearance of NaCl is 10 molars per second. Wonderful. So every second you're losing 10 molar per second. Technically it's a negative 10 molar per second. So question is, what is the rate of appearance of NO? Well, you notice the ratio of NaCl to NO is 1 to 1. So guess what? The rate is going to be the same. So as fast as NaCl disappears, NO appears. Would it be the same for Cl2? Of course not. Cl2, if you do the math, let's do it real quick. So you have 10 molar per second for every 1 to 2 moles of NaCl. You produce 1 mole of Cl2. So your rate of appearance of Cl2 is 5 molar per second, which makes sense. You're producing only 1 mole of it and using 2 moles of the reactant to produce it. So of course the rate's going to be smaller. You can see how the math works out. So important to note that if you have the rate of one chemical in a balanced reaction, you can figure out the rate of all the others with just that information using stoichiometry. So another way of using stoic, which makes it even more fun. All right, rate laws shows the impact of concentration change on reaction rate. What a rate law is basically a formalistic representation of a reaction that would help you determine what would happen if you change the concentration of a particular chemical. Would the rate go up, down? This is the information. That is the whole point of a rate law, to tell you the impact of concentration of chemicals and how fast the reaction goes. So here's a generic reaction. Here's a generic rate law. What you'll notice is that the chemical A and B, those are reactants. So there's no products in the rate law. I want to make that clear. It's only reactants. Is raised to these exponents. Now these exponents are not little a and little b, so it's not the coefficients. You have to determine these through data, and that's what we're going to be talking about. So for example, if x equals 1 and y equals 2, then the rate law is rate equals k, a to the first, b to the second. There's only 3 options for your orders, which is what the 1 and 2 represent. They're called the rate orders. So the rate order is either going to be 0, 1, or 2. That's it. That's all your options. There's no 3, 4, 5, 6. So I want to cut to the chase and just tell you 0, 1, 2. Now, theoretically, there's fractions, but for the AP exam, there is no fraction, so we're not going to waste our time analyzing that. So if the concentration of A is doubled in this situation, the rate is doubled. And you're probably like, well, why is that? Because you're raising it only to the first power. So let's say your original concentration was, let's say, 2 and 2, right? Hypothetically. Let's say right now the rate would be 2 squared times 2, which would be 4 times 2. Your rate would be 8K basically, right? All I did was plug in the values and I got that number. And I just kept K as is. K is a rate constant. We'll talk about it a little bit. Now, what if I double this? Just say, instead of having 2, I make it 4. I double the concentration. B is still going to be the same. So this is going to be 2 squared. So now, 2 squared is 4, just like it was before, right? But now you're multiplying times 4, which gives you 16. So what happens to your rate as a result of doubling the concentration of A? It doubles. It goes from 8K to 16K. That's what the rate law tells you, is what happens if you change the concentration. And by the way, your 3 options are 0 order, 1st order, 2nd order. If concentration of B is doubled, the rate will increase 4-fold. And you're probably like, well, why? Well, you kind of get an idea, right? So we still have the same original AK in the beginning, but now we're going to double B. So B is going to be, instead of 2, we're going to make it 4. So 4 squared is equal to 16, right? 16 times 2. Why 2? Because we're just going to keep the concentration the same. So we have 2 times 16, which is equal to 32. Okay. How did I do it? All I did was plug in 4 instead of 2 over here, squared it, because that's what we have to do mathematically, and just kept the other one as 2. And as a result of this, I got 32K. Now, what does that mean? Well, I started at K, that was the original rate. Now I'm at 32K, right? By what value did the rate increase? By a factor of 4, right? Because you went from 8 to 32. So that's where you can basically theorize ahead of time. You don't need to sit there and do the calculations. You can assume that if it's a first order, if you double the concentration, your rate doubles. If it's second order, you can assume the concentrations go up by a factor of 4 automatically, guys. There's no analysis, no thinking, just that's what it is. I'm showing you the math to show you why it is, but do you need to sit there and do the math problem? No, heck no. Well, if it's zero order, then that chemical has no impact on concentration. So if you double the concentration of a chemical and there is no effect on the rate, it's zero order. That's a way you could tell it's zero order. Overall reaction order, all you do is just add up your exponents or your orders in a situation. So the overall order for this scenario is 3, 1 plus 2, because A is to the first, B is to the second. All right, so now let's look at the math. This is where it gets entertaining. So what you need to do to forget the rate law is to use this kind of experimental data. And the system is very, very specific. So what you're looking for, if I want to figure out the rate order for C, I'm going to look to see where C is changing and A and B are being held constant. So what does that mean? You notice in experiment 1 and 2, you see how C is 0.2 and 0.1 the concentrations? That's what I'm looking for. And you see how A and B are both 0.1 both times? That's what you want. You can figure out the rate order for C using experiment 1 and 2. And just to be clear, because for some reason students think that the two reactions you're picking, two experiments have to be right next to each other. No, they don't. It can be any experiments you want. It could be 1 and 4, 1 and 3, 3 and 2. It doesn't matter. Just pick the one that makes sense. So for C, I'm going to use experiment 2 and 1. I'm going to put 1 over 2 to be exact. And the reason is I don't like fractions. 0.2 divided by 0.1 is 2. 0.1 divided by 0.2 is a half. I don't want to deal with fractions, so I'm not going to do it that way. So a little shortcut for you. All right, what if I want to figure out A? Remember, what you're looking for, the concentration changing. You see how 4 and 3 do? And you notice that B is the same in both experiments. Perfect. That's what I'm going to use for A. I'm using experiments 4 over 3. And then for B, same thing. What am I going to use? Well, can I use 3 and 4? No, staying the same. Can I use 3 and 1? No, because even though A is staying the same, C is not. That's going to create a headache for me. So what I'm going to do instead is pick 3 and 2. Why? Because the concentration changes for B, but not for A and C, and that's what you want. So let's see how the math for this works. So for A, and it's extremely important you do it this way. If you want to make sure you do this correctly every time, do it this way, write everything down. If you don't, you have to verbally explain the concept, and that's a headache and a half. You have no idea. So your best bet to do these kind of questions on the exam is just do what I'm just showing you right now. Put the whole experiment 4. All I did was take everything here, write it down, and I raised it to X, Y, and Z. You could pick any 3 letters, A, B, C, J, K, L. I don't care. Those are just variables. What I'm trying to do is solve for them. So I took experiment 4 over 3. You notice all these numbers. See the 0.1, 0.2, 0.1, 0.02. Perfect. Now what happens? Look at the math. Goes away, goes away. Now you're left with just 2 to the x equals 4. That's how the math plays out. And that's what you usually should get, some sort of manageable number. So what is x equal to? Well, if 2 to the x equals 4, then x has to equal 2. Remember, we only have 3 choices, guys, 0, 1, 2. So it's not going to be complicated, crazy math. So A is second order. We did all that work to figure out A is second order. And why do we do that? So you can figure out what the effect is going to be on rate when the concentration of A changes. What about for B? Well, we already decided which 2 experiments to use. We're going to use experiment 3 over 2. Notice I wrote everything down again. That's to avoid having to explain it. I don't want to do a verbal explanation. I hate those. How does the math play out? Goes away, goes away. 2 to the y equals 2. So guess what y equals? That's right, first order. Pretty simple. And then for C, concentration doubles from 2 to 1. Well, rate remains the same. So those are the 2 I'm going to use. Goodbye, goodbye. This is interesting. 2 to the z equals 1. So if you're really advanced in math, you know that if you raise 2 to the 0 power, or any number to the 0 power, you get 1. And that's what this is, a 0 order. So what does this tell you conceptually? That tells you that Z has no impact on the rate of the reaction. Even though it's involved in the reaction, whatever you do to Z is not going to matter. It's not going to change how fast the reaction occurs. It's always going to be based on the other two chemicals. So the rate law for this is rate equals K, A to the second B. What happened to C? 0 order. Can you put C to the 0 order? Yeah, of course. You can put C to the 0 and put that as part of your answer. That's fine. But you don't need to. So what's the overall order now? 2 plus 1 is 3. Now, the last thing you need to do is be able to calculate the rate constant. So the rate constant should be the same for every single experiment. So those 4 reactions you saw, all of them have the same K. Little k is all the same. What's the only thing that can affect little k? The only thing that can affect big K, temperature. That is it. Nothing else can do anything. So to solve for K, all we're going to do is take any experiment we want. In this situation, I think I took experiment 1, and just plug in the numbers. So I plugged in the rate, I plugged in A to the second, B to the first, did the math, there's my rate constant, which is 10 m to the negative 2 s to the negative 1. So for this, there's a shortcut. And I should show you the shortcut before I move on with it. So you can actually figure out what the units are for this really easy, because they're going to give you a point for the answer and 1 point for the unit. You could sit there and do the cancellation, which is fine, or do this. 1 minus the overall order. What's the overall order for this reaction? 3, right? What does that give me? Negative 2. What the heck do I do with a negative 2? That's going to tell you your exponent for molarity. So m to the negative 2, s, the time is always going to be to negative 1. I do want to make clear, time can be in hours, minutes, seconds. So please don't always assume it's s to negative 1. It could be hours to negative 1, minutes to negative 1, days to negative 1. Let the units in the question guide you for this part. But it's always going to be time to negative 1. That's never going to change. And this little shortcut here allows you to figure out the molarity value, which in this situation is negative 2. Makes it a lot easier. All right, using graphs to determine the order of the reactants. For first order, what you're looking for is concentration over time gives you a curved line. So you just have to memorize this. So if you see concentration over time as a straight line, this is called first order. The other thing that you want to note about first order is that you can actually determine the half-life based off it. So this is about 150. Half-life is half of that. So what's 1/2 of 150? 75, right? So 75 will be right around here somewhere. So you can figure out the half-life. So the half-life for this, if you look at the graph, is probably about what, 12, 13,000 seconds. So in another 13,000 seconds, which is about here, you expect it to be half again. So what's half of 75? That's about 37.5, so around 37.5, and that's exactly what happens. So a little piece of information you get from the graph, just FYI. Also, if you do ln of pressure, concentration and pressure are interchangeable. They use pressure for gases, they use brackets or concentration for chemicals and aqueous solutions. That's the difference, but same conceptual angle for it. So if you do the natural log of it, for first order, you always get a straight line. So if you don't get a straight line for ln, it's not first order. What is it, you ask? Well, let's take a look. What if you do ln of concentration versus time, you don't get a straight line? This is not a straight line, this is curved. Look at this. Look at this. I know it's kind of hard to see, but it's a little bit curvy. This is second order. The really simple way of determining second versus first, in case you're like, well, that ln looks pretty similar. Look at your data. Whenever they give you 1 over concentration over time, that is always going to be representative of a second order reaction. That's the graph for second order. So anytime it's 1 over concentration versus time, like, oh, I have second order. Have a nice day. And the last one, 0 order. 0 order, look at this one, concentration versus time, going up, positive slope. This is curved. It's not a positive slope. For 0 order, instead of it going up, it goes down. So the concentration goes down over time. And whenever you see that, that's 0 order. All right, half-life for first order reactions. There's the formula. You'll need to use it. K is the same K we just saw a second ago. It's called the rate constant, not to be confused with big K, which is equilibrium constant. So now that you have your rate constant, you're just going to plug and chug. So for this one, that gives you half-life is equal to 0.693 over K. Then you do the math, and you get 1.4 times 10 to the 10th year. That's your half-life. That's how long it takes to get to half of whatever you started. That's what half-life represents. The amount of time it takes to get to half of whatever amount of chemical you started in this scenario. We can go over elementary steps. So some Kinetics questions have what's called the mechanism, which is basically multiple steps, kind of like Hess's law, that show you how the reaction occurs and gives you individual reactions that add up to what should be the final. These are called the elementary steps. The one cool thing about these elementary steps is that your rate law is equal to the coefficient in the reaction. So usually you do rate law like we saw a minute ago with experimental data, but here what you can do is that this tells you that A is to the first and B is to the second. So your coefficients become your exponents, but this is only valid, once again, only valid for mechanisms. So if you don't have multiple steps, it's not a mechanism, you can't do this. See here, it's first and first, 3. You have just G. The things you need to be able to recognize from this is where some characteristics. So first off, you need to know what the intermediate is. Intermediate is a chemical that shows up as a product first and then ends up as a reactant later. So if you notice C, see how C in step 1 is a product and in step 2 it's a reactant? That's called intermediate. So C is equal to intermediate. Do we have any other intermediates in here? G also. Any others? Doesn't look like it. F doesn't. E, obviously no chance. The other chemical you need to be familiar with is called a catalyst. A catalyst shows up first as a reactant and later as a product. So A, not so much. And it cannot be one of the chemicals from your overall reaction. This is your overall reaction. A and B cannot be your catalyst. That's just guaranteed. So what is my catalyst? Well, see how D shows up as a reactant and then D again as a product. So D is considered my catalyst. Now, one thing I do want to make clear about this, when you're looking at mechanisms in particular, the way you justify this, like, how do you know it's intermediate catalyst? You would say in step 1, C shows up as a product, and then in step 2, it shows up as a reactant, thus intermediate. That's all you have to state. Just state where you saw the chemical, where you saw it, and then as a result, it's intermediate. Catalyst, same thing. D showed up at step 2 as a reactant, and then later in step 3 as a product, thus it is a catalyst. That's all you have to state. All right, determine the rate determining step for the reaction with the identity of the intermediates and catalysts along with an explanation. So the thing about this is your rate law. So whether they give it to you and you calculate it, doesn't really matter. But what you want is whichever of these steps has the exact same rate law. That is going to be considered your slowest step. The slowest step is always going to have the same rate law as the overall reaction. So if we go through this, the first one's rate is going to equal to K squared. Well, this is already my slow step. I don't need to go any further. I'm going to go through it just to show you how to do the rate laws. So it's K, G, C. That's going to be a fast step. How? Because it's not a slow step. If it's not slow, it's fast. Next one, rate equals K D B squared. And the last one, rate equals K H. So they're asking you for identification of intermediates. So let's take a look at intermediates. What shows up as a product, there's an intermediate, D, intermediate, that's it. Why isn't H? Is H intermediate? If you look at it, a little harder to identify, right? Because it shows up here and it shows up here. It's not part of the overall reaction. That's what's going to count as an intermediate. If this was like F, you couldn't do that. And let's see what else we have. Catalyst, Definitely can't be A. So even though A shows up as a reactant here and later as a product, that can't be a catalyst. Why? Because A is in the final reaction. You can't have a catalyst in the final reaction. It just doesn't happen. What about G? Yeah, there we go. G is a reactant, then a product. That's a catalyst. Any others? No, that's it. So that's how you identify them. All right. What is a catalyst? In case you're wondering, this is a reaction profile. What it shows you is that in order to start the reaction, you have what's called the activation energy. This is the activation energy. Every reaction has a minimum energy to put in to start the reaction. That's called the activation energy. So for this one, it's pretty high. If you're trying to go prox reactant, it's even worse, because look at the activation energy for the reverse reaction. It's from here all the way here. And just to be clear, activation energy is from the reactants to the top of the hill, not from the bottom. Okay, not down there. Reactants top of the hill. What a catalyst does, it provides a shortcut, if you will, lower activation energy. So instead of requiring this much, what a catalyst does is, hey, you don't only need this much. You can cut through the mountain. And that's what it does. Now, I do want to make clear the catalyst also works for the products. So it will lower the activation energy going to the products, but also the products going to the reactants as well. So both of them are going to have a lower activation energy. Now, one other detail you want to note about this, the distance between the reactant and product is called your enthalpy. And for this one, hopefully you can see it's exothermic. Why is it exothermic? Because you're releasing energy. You're going from reaction to product, you release energy to get there. That's all the data you should be able to interpret really quickly from a reaction profile like that. All right, so here's some examples. X in this situation, you see how the products are higher than the reactants. This is endo. Lower, exo. Lower, exo. Which one has the lowest activation energy? This one. Which one has the lowest activation energy for the reverse reaction? How do I know it? Look at the hill. Look how short this hill is compared to all these other mountainous journeys. This hill is actually shorter than the reactants to product. It actually takes less energy to make it go from products to reactants than it is to reactants to products, which is kind of funny. So catalysts lower the activation energy and increase the rate of reaction. Each hump you see on these reaction profiles represents a step in a mechanism. So this particular catalyst reaction has 2 steps. So it's a 2-step pathway, just to make note of that. And you can see another example of it. You see there's 1, 2 humps, 2-step mechanism. First reaction, exothermic. Second reaction, exothermic, because it's lower each time. Here's exothermic again, lower. See how distance going down, going up, endo. You can see the activation energy for this one's down to the lowest one, going from products to reactants. All right, question, consider the following potential energy diagram. Which letter shows the activation energy of the uncatalyzed reaction? Well, remember, uncatalyzed is going to be from reactants to the top of the hill. Now, if you pick C, that's not the activation energy. That serves as a mess with you. That's nothing useful right there. So the correct answer is A. Now let's do the other ones for sake of fun. What does D represent? If you look carefully, basically the distance between reactants and products. That's your enthalpy. And what is this one? That's right, endothermic, endo. That's pretty much all the main data that we want to talk about for now. All right, environmental concern is the depletion of O3 in the Earth's upper atmosphere, where O3 is normally in equilibrium with O2, and O. Proposed mechanism for the depletion of O3 in the upper atmosphere is that, right, to balance chemical equation for the overall reaction represented by step 1 and 2. All you have to do for that, bring it down like you would do Hess's law. ClO, have a nice day. Cl, have a nice day. O3 plus O produces 2O2. That's all it is. Now, if you look at it, you can kind of tell there's a catalyst in there, right? So what's the catalyst? Cl, exactly. Shows up as a reactant in step 1, then as a product in step 2. And that's my justification too, 2 for 1. What's my intermediate? ClO. And there's those questions. So ClO is a catalyst, and the reaction is a reactant in step 1, or appears as a product in step 2. See how easy that is? You can't screw that up. All you have to just stipulate is where it is. Clear identified the intermediate. We already identified that too. ClO is the intermediate. It is a product in step 1 and pure is a reactant in step 2. If the rate law for the overall reaction is found to be rate equals KO3Cl, determine the following. Overall order of the reaction, 1 plus 1 is 2. That's your exponent. Remember, that's your orders. If you don't see a number, you assume it's 1. So 1 plus 1 is 2. Appropriate units for K, what's 1 minus 2? That's right, m to negative 1. And the units for time for this, I believe was, they didn't give it to you, so you just call it time to negative 1. See how that is? Shortcuts, that's what it's all about. The rate determining step of the reaction along with the justification of your answer. So the rate determining step must have the same rate law as the overall reaction, which in this situation was step 1. The coefficient of the reaction in step 1 corresponds to the exponents of the species concentration in the rate law. Pretty easy. That was kinetics in a nutshell.